Hello. Today I'd like to talk to you about pH calculations with acids. We're going to take a look at a lot of different acids. First, strong acid pH calculations. We're then going to move on into weak acid pH calculations. And finally, we're going to talk about some different acids that are called polyprotic acids and also talk about their calculations as well. So the whole motivation behind this is that in order to measure the strength of an acid, we often use the pH, the power of hydrogen ions that we've talked about previously. Now, for strong acids, for calculating their pH, we have to remember that a strong acid, let's say we have a strong acid, HA, goes to completion and completely ionizes to make H plus and A minus in solution. And so, however much HA I put in a beaker, let's say I know the concentration of HA in my beaker, because this goes to completion, that's going to be equal, it's my initial concentration, is going to be equal to the concentration of H plus, and it's going to be equal to the concentration of A minus after my reaction has gone into completion, my dissolution or my ionization here. So for any strong acid, I can determine the concentration just by looking at these two values here. For example, what is the pH of 0.015 molar HCl? Well, I know the concentration of my HCl is 0.015 molar, and that's going to be equal to the concentration of my H plus. Now remembering that pH is defined as the negative log of my hydrogen ion concentration. The pH of this solution is going to be negative log of 0.015. Plugging those numbers into my calculator, it looks like I get a pH of 1.8 for our 0.015 molar HCl solution. Go ahead, try this yourself here with our pH of a 6 molar hydrochloric acid solution, which is about half as strong as it can possibly be. The maximum HCl concentration is about 12 normally. So go ahead, give that a try, and we'll take a look at it here. So to find this pH, once again, I know my concentration of HCl is 6 molar, so my pH is going to be minus the log of my H plus concentration, so it's minus the log of 6.0 molar, and when I plug those numbers in my calculator, it looks like I get a pH of about negative 0.78. Now, it is perfectly okay to have a negative pH. That just means that this is a very, very strong acid solution. The pH scale we commonly see goes from 0 to 14, but negative pHs are possible, and it looks like HCl can just hit that negative here if you had a 6 molar concentration. So for strong acids, it's fairly simple. Just know the concentration of the acid, you know the concentration of the H plus ion then, and then you work the math from there. For weak acids, it's not going to be quite as straightforward because we have to remember, for weak acids, they consist in subsist in a equilibrium reaction. And so if I have some weak acid, HA, it's going to react with water and exist in an equilibrium between H3O plus and A minus. And so I'm going to get my acid dissociation constant, Ka, to be equal to H3O plus times A minus divided by my concentration of HA. And so to solve for the equilibrium concentration of H3O plus, I'm going to have to use one of our old friends, the ice table. And so here we have a problem. We have what is the pH of a 0.2 molar solution of HCN. Now, oftentimes you'll see we won't give you the Ka. If you're not given the Ka, just know it's going to be in your textbook back in that Appendix C. You can look up tables of common acids and bases. So the Ka, if you look it up back up in the back of your textbook, the Ka for HCN is 6.2 times 10 to the minus 10th. So now that I have the Ka, I can go ahead and start setting my ice table. So just like we've seen before, I, C, and E. The water's not going to play a factor here, so it's going to be between HA, H plus, and A minus. Initially, I have 0.20 molar HA. I have 0 H plus and 0 A minus. To change to equilibrium, I'm going to lose an X amount of my HA and gain an X amount of both of my H plus and A minus. And this is just because of the stoichiometry. It's 1 to 1 to 1. So I have a 1-to-1-to-1 ratio here between my x's. And then finally, we can write the equilibrium expressions as 0.20 minus x, x, and x. So if we were to write out our equilibrium expression here, we know that it's H3O plus times A minus divided by HA. And so plugging in my values here, I'm going to have 6.2 times 10 to the minus 10th is equal to x times x divided by 0.2 minus x. Now, this solution is a weak acid, and something that we can use as an approximation for a weak acid is that this x is going to be very, very small. Not very much of it is going to dissolve. We don't really like to solve this out here because there's this 0.2 minus x on the bottom. This means that I'd have to solve a quadratic equation. We can instead use an approximation by if we assume that x is very small. Well, then 0.2 minus x, if x is very small, is essentially 0.2. So we can assume x is very small and assume that the concentration of my acid, HA, at equilibrium is approximately equal to the initial concentration. We're basically saying that very little of my acid is actually going to break up and dissolve in solution here. Now, in order to do this, we have kind of a criteria or a rule we can use to determine when we can make this what we call small x approximation. We can do this when the concentration of my acid, so we're going to say the molarity of the acid divided by the Ka, we can do this when that's greater than 100. Essentially, when it's 2 powers of 10 greater than the Ka. Here, I'm going to have 0.2 divided by 6.2 times 10 to the minus 10th. That's a very, very big number, much greater than 100, and so it's okay to make this approximation. If you'd like, you could go ahead and try this using the quadratic formula and see if you get an answer that is very similar to the answer we're going to get here. Now to solve this out, I'm assuming that 0.2 minus x is essentially just 0.2. So that simplifies my equation a lot. If I come down here, I'm going to end up getting 6.2 times 10 to the minus 10th equals x squared divided by 0.2. When I solve that out in my calculator, I get an x equal to 1.1 times 10 to the minus 5th molar. Now that x is not my final number because I'm asking for the pH of my solution. So now I know what x is, that's my H plus concentration. Now to find my pH, I'm going to have to take the minus log of that number, 1.1 times 10 to the minus 5th. And when I do that, it looks like I get a pH of about 5.0. Now something you should notice is that this pH is a lot greater, a lot higher, less acidic than those strong acid pHs we saw. And that's because very little of it dissolves into solution. And so a pH of 5 is much more reasonable for our weak acid here than it would have been for our strong acids we saw previously. And finally, let's go ahead and take a look at our polyprotic acids here. In dealing with polyprotic acids, we first need to define what a polyprotic acid is. So a polyprotic acid has multiple acidic hydrogens. As you've kind of seen so far, not all hydrogens on a molecule are able to participate in acid-base chemistry, but there are some acids that have multiple hydrogens that fit this bill. And so if we take a look at some examples, H2SO4, sulfuric acid, H3PO4, phosphoric acid, and H2CO3, we see that all of these have multiple hydrogens written out front in their structures, and all of these hydrogens can be used to donate to water or some other base in solution. Now, when we're thinking about this, we want to think about the equilibria that are involved in each of these reactions. And so let's go ahead and take a look at H2CO3 a little further. So for my first equilibria, my H2CO3 is going to go ahead and donate a proton to a water, and then it's going to form its conjugate base, HCO3, and that's going to liberate an H3O+. Now this is going to have a Ka associated with it, and if you look up the Ka for the first proton, so we're going to call it Ka1. The Ka for the first proton from H2CO3 looks like it is 4.4 times 10 to the minus 7. So like we've said before, H2CO3 is a weak acid. We can tell that by the Ka. It's very low, but it's still going to lose a proton here and donate to be an acid in solution. Now, what can happen is that this HCO3 minus can still act as an acid. If we imagine that happening, that HCO3 minus is going to donate a proton to an H2O, and so that would be in equilibrium then with CO3 2 minus and an additional H3O plus. Now, if you measure the Ka for this one, Ka2, that's going to be a little lower. It's about 4.7 times 10 to the minus 11, essentially 4 times lower, 4 powers of 10, than the Ka for the first proton. Now, this makes sense because it's a lot easier to lose your first proton than it is to lose your second. This molecule right here is currently negative, and so there's more Coulombic electronic attraction between that H plus and that minus for this ion than there is for our H2CO3. And so typically for nearly every polyprotic acid you're going to see, the Ka is going to decrease as you continue to lose hydrogens because those hydrogens are more likely to stick onto their parent molecule. Now, we can still do calculations for pHs with polyprotic acids, and it actually ends up being pretty easy to do. The reason why is because this Ka is very, very small. And so because of that, we can normally assume that all of the H3O plus concentration comes from the first ionization. Let's go ahead and see what that might look like here. And so if I go ahead down here, set up an ice table for the first ionization of my carbonic acid, we're going to go ahead and have H2CO3. That's going to form H plus and HCO3 minus. I have I, C, and E. Looks like my I here is 0.1 molar. H plus and HCO3, we're going to say start at 0. I then lose an X amount of this, gain X and X, and so I get 0.1 minus X, X, and X here. And once again, I can see, because my acid concentration is so large compared to my Ka, I can once again make this small x approximation. So we're going to say that this amount minus x is insignificant compared to the 0.1 molar H2CO3 that we have in our solution. And so when I set up my Ka expression, my Ka, which is 4.4 times 10 to the minus 7th, that's just going to be equal to x squared divided by 0.1. When I do that, I end up getting an x equal to 2.1 times 10 to the minus 4th molar. Now that's my concentration of H plus and HCO3 minus after the first ionization. Now, like I said, we could go ahead and assume that this is where the pH comes from because we can assume that all H3O plus is basically from the first ionization because this equilibrium constant is so much smaller than the other. But let's go ahead and say we didn't want to assume that. Let's go ahead and try to prove that that doesn't matter. So to do that, we would set up a second ice table, realizing that I know the concentration of HCO3 minus initially. I know that after this ionization, I'm going to get 2.1 times 10 to the minus 4th amount of x. And so I can go ahead and plug in 2.1 times 10 to the minus 4th as my initial concentration of HCO3 minus. Now that HCO3 minus is going to break up into H plus and CO3 2 minus. I still know my concentration of H plus. It is also x 2.1 times 10 to the minus 4th. And we're going to assume that the CO3 2 minus is 0. Now here, it's going to shift again to the right because I have 0 CO3 2-, and so the cube is still 0, and so it wants to shift to the right. Once again, I can still see that I have that factor of 100, that 2 powers of 10 factor here, so I can make the small x approximation and say that the equilibrium concentration of this is going to be 2.1 times 10 to the minus 4th. If this is x and this is x, then I can set up my Ka expression from here. Ka2 is 4.7 times 10 to the minus 11th. That's going to be equal to x squared divided by 2.1 times 10 to the minus 4th. And if I solve x out here, I get 9.9 times 10 to the minus 8th molar. So to find the total H plus concentration then, all I would need to do is add the two x's, my two H plus concentrations from each of my ionizations. Well, if you do that in your calculator, 2.1 times 10 to the minus 4th plus 9.9 times 10 to the minus 8th is essentially 2.1 times 10 to the minus 4th, seeing our number of sig figs here. And so then I can finally just use this number as my H plus concentration. So to find my pH, I'd go ahead and plug in minus log of 2.1 times 10 to the minus 4th, and that's going to end up being 3.7. So for polyprotic acids, what we've seen is that you can just assume that that first ionization is going to be the major contributor and just do this like another weak acid concentration. Okay, that's been calculating pH of strong, weak, and polyprotic acids. Thank you all for listening. Have a great day.